Hey everyone, so we are the Storm Chasers, and today we're going to be talking about outage predictions in North Carolina. So right off the bat, our mission is to provide reliability whenever we face nature's unpredictability. And one of the main ways we do this is by forecasting storm outages by looking at different types of severe weather events. And down here, you can meet our team, Dominique, Sunil, Lee, and me. So how to best use our model. So the purpose essentially of our model is to predict the number of utility assets that go out due to severe weather. The way that we end up measuring the accuracy is by using the mean absolute percentage error, or MAPE. And MAPE's frequently used because of its easy interpretation, and it's typically calculated by determining the average magnitude error that's produced by the model.
With the first step towards our model development, we kind of used initial exploratory data analysis along with feature selection, which Lee will talk about more in a couple of slides, hand in hand to figure out which would be the most impactful features that the model can learn from. And what we tried to do with the EDA side of things is to find out features that had a direct impact on our target variable, the outage count. So here are two examples of features that we ended up finally including in our final training set. And as you can see, both CAPE, which stands for convective potential, available potential energy, and LU2430, which stands for land units, have a direct relationship with the outage count in that as both of them increase, the outage count decreases. And looking at the other side of things, where we've looked at features that don't have such a clear relationship with the target variable outage count, we didn't include these purely for that reason. And as you can see here, this regardless of the magnitude of both these features, canopy interval and length proxy, they don't really seem to have a correlation with how they affect the outage count. And so we didn't end up using them. Finally, just to get an idea of the distribution of our outage count variables, we plotted the count against the outage count, and we found that storms who resulted in zero outage counts were off the charts. They were exponentially higher than the rest of them, and we did deal with them, which we'll also talk about later on.
For the feature engineering part, we examine all the features and find some non-numerical features. For the categorical feature, event type, we conduct one-hot encoding for this feature. And besides, there are some features are comprised of string list. We decode the numbers in the string list as individual extra features. And for the daytime features, we conduct sine and cosine periodic encoding of the date and of the date seconds computed from the earliest date in that daytime feature column. And for our feature selection tools, we choose LightGBM as our base model. It's a boosting tree method that can perform feature selection during the training process. And we choose Optuna as our hyperparameter optimization library. Optuna is much better than grid search. It's more time-consuming, time-saving, and optimal. Since there are more than 4,000 features, we decide to train our model on GPU with feature rights. And here is our feature selection pipeline. We define our objective for optimization as mean absolute error of the 5-fold cross-validation. And we run 200 trials in total to find the final hyperparameter, and we input the best hyperparameters into the GBM to output our feature importance. Here's the top 30 feature importance generated from the Optino GBM trained on our training site.
Yeah, so in the end, when after going through both EDA and feature selection, we selected 15 features that we felt were the most important in terms of the weight they held, as well as how directly they impacted the outage count variable. And we also wanted to make sure before going ahead with modeling with these features that they weren't heavily correlated, and including them would throw off the model or have it be redundant. And so in order to do that, we plotted a correlation matrix with the 15 features we chose. And as you can see, most of them were very uncorrelated, and even the ones that were correlated weren't as high as they could have been. And so we went ahead with these 15 features.
So these were the final features that we ended up using, and there's 15 of them. And particularly looking at number 1 and 4, the fuse counts and breaker counts. The fuse counts and breaker counts are very important because they look at the health of the electrical system. And the fuse counts particularly looks at potentially how many fuses have been blown due to severe weather. And the breaker counts could potentially be looking at the number of times the circuit breakers have been tripped. The poly EWKT0 variable potentially gives us the geographic location of, or the geographic layout of the power grid, which is good for spatial analysis. The LU2430 code is potentially a land use code, correlating a specific area that has been impacted by the severe weather. CAPE is a very, very typical acronym that's used to measure the atmospheric instability. It's a very good predictor as to whether there's going to be how the severe weather is going to impact the power lines. And from 10 to 15, we see that there's different wind speeds at various intervals located in Lambert, North Carolina. Wind speeds are a very, very common source that leads to power outages and power disruptions. Dominique is going to talk a little bit more about why having a better foundation and domain knowledge in these features would be very, very important.
So we wanted to choose models that we used in class and compare their performances. We compared lasso, ridge, decision tree, and random forest. And also shown here, we compared performance using downsampling and without downsampling, which I'll explain next why we experimented with this in the first place. And in the end, our best performing model was random forest with downsampling. Our hyperparameters included a max depth of 344, min sample split of 4, and min sample leaf of 8. So our final MAPE value for our random forest model was 19.7%. And we recognize that though this is a solid MAPE value, we still have room for improvement to provide even better predictions in the future. So we think one main reason, or one main way we can improve our model was to increase our domain expertise with regards to the features. So given that we had over 4,000 features, and without the domain expertise, we had to heavily rely on our feature selection process and EDA without additional consultation and verification from an expertise perspective as to what these features meant and how they exist in correlation with one another. So having expertise could significantly help us in the future. So in terms of challenges and resolutions, a big issue that we ran into is the 0 values for outage count. With the use of MAPE, a metric that has the actual value as the divisor, this caused our initial runs of our model to have a MAPE value of infinity, which is obviously not useful or helpful in the slightest. We quickly realized the issue, and to resolve it, we did transformation on our target value by adding 1 to all of them. We chose to do this because as we are predicting outage counts, a whole number makes the most logical sense to add to our target value. So by adding 1 to each of the outage counts, we were able to actually produce useful and interpretable MAPE values for our model. And then also, as Sunil mentioned before, and as I showed on the model experimentation slide, we had a very skewed distribution in our target value. So to address this challenge, we downsampled our 0 group of target values to be the same number as non-zero. And this, as we showed, helped our overall model performance. So that is all for our presentation for our team's model. Thank you again for watching.